Okay, today we're going to look at gases. For our calculations on gases, we're going to need to know how to do some conversions. The first conversion that we're going to look at is a temperature conversion. So for the calculations with the gases, we need to convert from Celsius to the Kelvin scale. So Celsius is the one that we usually use in our everyday lives. You might say it's 20 degrees Celsius on a nice day here. So we don't usually use Kelvin to describe that temperature or the temperature of an oven or anything like that. So it is probably new to some of you. So 0 degrees Celsius, which is freezing temperature for water, is 273 Kelvin. 50 degrees Celsius is 273 plus the 50, 323 Kelvin. Okay, so to convert from Celsius to Kelvin, all you have to do is this: add 273, and that's it. Just like 0, convert to Kelvin. I added 0 plus 273, and that gave me 273 Kelvin. 50 plus 273 gave me 323 Kelvin. So minus 273 degrees Celsius, what would that be in Kelvin? It would be 0 Kelvin. Okay, so that's all you have to do. And it is just a 1 degree change, no matter what. You know, it's 0 degrees Celsius up to 1 degree Celsius. So like 0 degrees Celsius up to 2 degrees Celsius is the same as 274 Kelvin up to 275 Kelvin. There is still just 1 degree of a change. The next one then is pressure. Okay, so temperature can affect gases, and pressure can affect gases. So we need to know the conversions. And the next one after pressure is going to be volume. So they're the 3 properties that we're going to look at in terms of gases today. So pressure, we might know already from junior cert, the formula for pressure is force over area. Now the units, force, what's the unit of force? It's the Newton. And the unit of area is the meters squared. So usually it's written as n/meters squared, or n to the minus 2. Okay, but we can also call that unit, the Newton meter squared, the Pascal, PA, capital PA, Pascal. The normal atmospheric pressure of a gas is 1 by 10 to the 5 Newton meters squared, or 1 by 10 to the 5, and the other unit that we can call it is the Pascal. Okay, and it doesn't matter which one you use, but as long as we just want to keep the units the same at the very end of the answer. So just be wary of which one you're using. They're the exact same thing anyway. Now volume. Okay, so volume. When we're talking about drinks, let's say, we might say a litre of Coke or a litre of milk or something. 1 litre is 1,000 centimetres cubed. A half a litre is 500 centimetres cubed. And 1 litre can also be written as 1 dm cubed. So just be careful with that, because sometimes in the exams they can write it as dm cubed and you might be a bit confused with what that is, but it's just another way of saying litre. So they might write down 1.5 dm cubed, and that'd be 1.5 litres, or 1,500 centimetres cubed. Okay, so there are conversions. Now something else that we might see in these questions ahead is this. So in your question you might see at standard temperature pressure, STP, standard temperature and pressure. So what is the standard temperature and pressure? Temperature is 0 degrees Celsius, which is 273 Kelvin. Pressure would be 1 by 10 to the 5 pascals, or you might see it written as 100 kilopascals, either. Okay, so the minute you see in a question at standard temperature and pressure, that's telling you already two pieces of information: the temperature and the pressure of the system at that moment in time. Okay, let's look at Boyle's law. So we're going to look at two laws, Boyle's law and Charles' law. These two laws govern the formula that we're going to use to do our calculations. So Boyle's law states that at constant temperature, so we have, let's say, a system that has a certain amount of gas, a fixed mass of gas. If that fixed mass of gas was at a constant temperature, the volume of the gas is inversely proportional to its pressure. So if you change the pressure of the system, the volume will also change if you're keeping temperature the same, because you only want to measure the two variables. So that means that there's some relationship between volume and pressure, and they're inversely proportional, so that means the one goes above the P. So what does this mean? This means that if in a system, if the pressure doubled, okay, so I'm increasing the pressure here, the volume would half. Okay, so you can just imagine if I put in numbers, let's say, if I'm going to half, the pressure is going to be doubled, okay? So I'm going to say, see how I literally changed the P to a 2, doubled it, and imagine if it was a 1 originally, doubled the system, doubled the pressure. That's now showing that the volume is going to be halved. Okay, if I tripled the pressure, the volume is going to be down to a third. And that makes sense, because if you're putting loads of pressure on molecules and atoms, what you're going to do is you're going to actually just bring them closer together. So you're decreasing the volume that it takes up. You're decreasing the space that it can take up. Okay? So Charles's law then. At constant pressure, again imagine a system with gas molecules in it. The volume of that fixed amount of gas is directly proportional to its temperature. So that's saying that the volume is directly proportional to its temperature. So if I have a system with gas molecules in it, and if I increase the temperature, what that does is that it excites the atoms and they move around faster and they want to take up more room, okay? And that increases the volume. So an increase in temperature makes an increase in volume. Okay, so this is our combination of the two laws, taking in pressure, volume, and temperature. On the left-hand side, we have system 1. And on the right hand side, we have system 2. So we're able to distinguish between the two systems if I have a certain amount of gas and at a certain pressure and a certain temperature and it has a volume. If I change any of those attributes to the system, this formula will tell me what happens to the volume the second time around in the second situation. So I like to say that this is usually your current situation, and then over here would be your new system, and the volume of the new system would usually change because you either change the pressure of the system or the temperature of the system. So you're going to have a new volume. So let's look at an example of how to do one of these questions. Okay, so here's our question. The current situation is that we have a canister that's filled with hydrogen gas. It's kept at 20 degrees Celsius, 900 kilopascals, and takes up a volume of 75 centimeters cubed. And we want to know if we change the temperature and pressure to standard temperature and pressure, what volume will the gas now take up? So one rule of using this formula is that the temperature must be in Kelvin. Okay, so how I like to go about this is just I write down current and new situation. And I just take the important pieces of information out of both of them and make sure my conversions are done. So the temperature, 20 degrees Celsius. You have to add on the 273 to get it into Kelvin. And you're going to end up with 293 Kelvin. Okay, the pressure, it's in pascals, kilopascals, that's perfectly fine. As long as that we use kilopascals on the new section as well. The volume is 75 centimeters cubed. That's okay, as long as the other new side is also in the exact same units. Temperature. So our standard temperature and pressure is 0 degrees Celsius, which is 273 degrees Kelvin. Pressure is 100 kilopascals, keeping the same. If it's kilopascals one side, it's kilopascals the other side. And the volume is the one that we want to know. So we're going to use that formula, the combination of the two laws. And you're going to fill it in with the current situation and then the new situation of standard temperature and pressure on this side. We don't know the volume, so we're going to keep that as V2. Now just with some maneuvering of the equations, you can find V2 on its own and you'll get the volume to be 628.92 centimeters cubed. Okay. And you can look at the pressures, the change in the pressure there. See that we've decreased the pressure. So that makes sense that the volume was very low at the start because it was under such high pressure. That it's now decreased the pressure, so the volume of the gas takes up a much higher volume. So let's go to the next one. Okay, here's our second example. So again, we have a canister of helium. It's taking up a volume of 5 litres at the moment, under pressure of 9.2 by 10 to the 4 Newton meters squared. So calculate the volume if the pressure is changed to 1.01 by 10 to the 5 Newton meters squared, And it says that the system is at a constant pressure. So, again, current and the new situation. So the current volume is 5 litres, and that's okay that it's in litres. Okay, as long as your answer is in litres, the same thing. The only thing you have to make sure it always change is degrees Celsius to Kelvin. Okay, pressure is 9.2 by 10 to the 4. And temperature, it doesn't say what it is, it's just that it's constant. So I'm just going to write K for constant. Volume here, we don't know. The new pressure, we do know. And the temperature again is constant. So we fill this in, 5 litres. I'm just going to write K for the temperature. Don't know the second volume, V2. And what can happen is that we can just get rid of the K's. They're both on the bottom at the end, and they're the exact same. So now with some movement of the numbers, we can get our V2. And the volume is 4.55 litres. Okay, if you want to give this one a go, again, this is one change to change the system, change to pressure, change to temperature, and we're going to figure out what the volume is. So you can pause now if you want to give that a go. Okay, we'll write down our formula, which is the combination of Charles' law and Boyle's law. So we're going to go straight and fill it in. 5 degrees, sorry, the volume, 1.2 meters cubed. It's fine as long as the volume comes out as 1 in meters cubed as well. Okay, make sure to keep the units the same. The pressure then, 101 kilopascals. Temperature, okay, so 5 degrees plus the 273, that is going to give you 278 Kelvin. The volume, we don't know. 108, the pressure is changed to 108. 30 degrees plus the 273, that's going to get your answer in Kelvin to be 303 Kelvin. And then we're just maneuvering all of this around. You should find your volume to be 1.22 meters cubed. Now what I mean by maneuvering this around, what you would do is you put this into the calculator, find an answer for it. Then, if it's dividing over here on this side, which it is under the line, if you bring it across, you're going to multiply whatever you got here by this answer, and then divide it by this. Okay, so you should be comfortable with maneuvering around equations to find out what one variable is. Okay, so now we're going to look at the gas and how it relates to moles and how we measure things in chemistry. So an experiment was done, and it was shown that 1 mole of gas, which is 6 by 10 to the 23 molecules or atoms or particles, that 1 mole of that gas took up 22.4 litres of space, of volume, at standard temperature and pressure, or at room temperature, RT, it took up 24 litres. So those two numbers are quite important to us if we want to figure out anything to do with mass, density, the mole, how many moles of that gas is present, because we immediately already know that 1 mole takes up that much space, depending on the temperature and pressure, of course. And that's backed up by Avogadro's law, which is here. that equal volumes of the gases contains an equal number of molecules under the same temperature and pressure. So if there are an equal number of molecules, let's say we had 6 by 10 to the 23 molecules of hydrogen and 6 by 10 to the 23 molecules of oxygen, and they were both at, let's say, standard temperature and pressure. Okay, so they're under the same conditions. They would be equal volume. Okay, it literally says that. So the same number of molecules under the same amount of temperature and pressure, they would have an equal volume. And the experiment showed that that volume is 22.4 litres for standard temperature and pressure. And you see this 6 by 10 to the 23 right here? That's Avogadro's number. And that means that 1 mole of H2 is present and 1 mole of oxygen is present. And it takes up 22.4 litres of space. Okay, so that's important for our little calculations now in this part. So this is our question. Calculate the density of ammonia at standard temperature and pressure. So let's break that down. Density. From junior cert, you should know that is mass over volume. So they're the two things that we need to get in order to calculate the density. So that's our guiding little piece of note and work that we need to get to be able to answer this question. What else do I know? Okay, standard temperature and pressure. That means it's 273 Kelvin and the pressure is 100 kilopascals. I may or may not need to use that, but I'm just breaking down the question into what I know. Ammonia, chemical formula, NH3. Okay, I can figure out what's the relative molecular mass of ammonia. So that's 14. And then hydrogen, and I have 3 of them. So that's going to give me 17. So that means that 17 grams of ammonia is 1 mole, because that's what the relative molecular mass tells me. How many grams of that substance will give me 1 mole of the substance. And it's a gas. So at standard temperature and pressure, 1 mole takes up 22.4 litres. Okay. So do I have mass and volume of ammonia? I have the mass of 1 mole and I have the volume of 1 mole. So yes, I do. So the density is the mass, 17, over the volume. And that gives you 0.76 grams per litre. And that's the ammonia, or density of ammonia at standard temperature and pressure. So I'll give you one now to do. Okay, so here it is. Calculate the density of ozone at standard temperature and pressure. If you need a hint, ozone has chemical formula O3. So you can pause now and try and find the density of ozone. Okay, again, density equals mass over volume. So how do I get the mass? Okay, so relative molecular mass, 3 times 16, because the mass of 1 atom of oxygen is 16, will give me 48. That means 48 grams of O3 is 1 mole of that ozone. Because it's a gas, 1 mole of the ozone takes up 22.4 litres. And I know that because it's telling me it's standard temperature and pressure. If it was room temperature, it would take up 24 litres. So I have the mass and I have the volume. So density is 48 over the 22.4. which is 2.14 grams per litre. Okay, here's the last little question. So we have 200 centimetres cubed of a certain gas at standard temperature and pressure, and it has a mass of 1 gram. Calculate the relative molecular mass of the gas. Okay, so write down what you know. 200 centimetres cubed, and we have 1 gram of the gas. Okay, so we need to find the molecular mass of it. So I need to bring it up to 1 mole of the substance. Now, I don't know how much of the mass is, so I can't bring it up to a certain number, knowing that that's going to be 1 mole of the compound that we're looking at. But seeing it's a gas, I know that 1 mole of a gas is going to be 22.4 litres, or 22.4 centimetres cubed. So I can bring it up to a litre on this side. And to do that, I'm going to bring it down, first of all, to 1 centimetres cubed. Okay, and all I've done there on both sides is just divided by 200. 200 divided by 200 is 1. That's where I'm getting the 1 from. And then 1 divided by 200. It gives me 1 over 200 grams. So 1 centimetre cubed of the gas contains 1 over 2000 grams. Now what I really want to get it up to is to get 1 mole of the substance, which is 22,400 centimetres cubed. So here I'm going to multiply both sides by 22,400 centimetres cubed. And I will get this now. And that's basically saying 1 mole of the gas has a mass of 112 grams. And because it's 1 mole, that amount of grams is the relative molecular mass of the gas. And that's it for this video.